This intermediate is called an oxaphosphatane. I told you there was a lot of cool names in this mechanism. Wittig reaction was first reported by Georg Wittig in the 1950s. He would eventually go on to win the Nobel Prize in 1979 for this reaction. In the classic presentation of the original Wittig reaction, it's a reaction of an aldehyde or a ketone to form preferentially a Z-alkene. The net reaction of the classic form of the Wittig reaction has an aldehyde reacting with the phosphorus Ylide to form predominantly a Z-alkene. Over the years since its discovery, there have been modifications and improvements to the Wittig reaction to make preferentially E-alkenes, or to work better with ketones, or to explore some of the other nuances of the Wittig reaction that are a bit beyond the scope of this video. Today, we'll deal with the classic form of the Wittig reaction, with the unsubstituted Ylide forming the Z-alkene. Before we get into the Wittig reaction itself, let's take a second to look at how to form the Ylide. The formation of the Ylide starts with an alkyl halide, and we react it with triphenylphosphine. The phosphorus of triphenylphosphine acts as a nucleophile, and the carbon of the alkyl halide acts as an electrophile. Phosphorus attacks carbon, displacing bromine, to form a new carbon-phosphorus bond. This forms an intermediate called a phosphonium bromide. There are lots of really cool names of intermediates in this reaction. To finish out the formation of the Ylide, the N-butyllithium acts as a nucleophile and takes the proton from the phosphonium bromide to form the new carbon-phosphorus double bond in the Ylide. This completes the formation of the Ylide. Anytime we need to form an Ylide, we can do so easily from an alkyl halide. Looking at the mechanism of the Wittig reaction then, we have our aldehyde and our Ylide. We know things about carbonyls. Carbonyls are electrophiles. They're electrophilic at carbon. They're electrophilic towards good, strong anionic nucleophiles, and an Ylide is a good, strong anionic nucleophile at carbon. So the step one of this mechanism is the Ylide acts as a nucleophile. Carbon gets to keep the electrons and attack the carbonyl, kicking electrons up onto oxygen in a nucleophilic addition step. I'm using a bouncing arrow here to show the movement of electrons, to show that it's the carbon that gets to keep the electrons to attack the carbonyl. If you're not familiar with bouncing arrows, I've got a very cool video on bouncing arrows you should definitely watch down below. This step follows the story of the carbonyls. Carbonyls are electrophiles towards good, strong anionic nucleophiles, and a good, strong anionic nucleophile can attack the carbonyl. If you're unfamiliar with the story of the carbonyls, I've got a separate video to tell you about the story of the carbonyls down below. The result of this step is the formation of a new carbon-carbon bond between the Ylide and the aldehyde. The result of this step is an intermediate called a betaene with an oxygen negative and a phosphorus positive charge. This carbonyl mechanism so far has been following the code of the carbonyls. If you don't know about the code of the carbonyls, you should watch my study tip video on code of the carbonyls linked down below. The Wittig reaction, though, is the one exception to the code of the carbonyls that proves the rule. The first step follows the code of the carbonyls, but from here on out, the Wittig reaction does not follow our code of the carbonyls. But I bet we can figure out what happens next. When I look at this intermediate, what I see is an oxygen with a negative charge and a phosphorus with a positive charge. That makes the oxygen look like a nucleophile and the phosphorus look like an electrophile. And indeed, what happens next is the O negative attacks the phosphorus positive to form a new oxygen-phosphorus bond. This intermediate is called an oxaphosphatane. I told you there was a lot of cool names in this mechanism. We call it an oxaphosphatane because atane is our suffix for four-membered rings, and this is a four-membered ring with an oxygen and a phosphorus, so we call it an oxaphosphatane intermediate. To finish out this mechanism, we're going to form the carbon-carbon double bond. To do that, we're going to break the carbon-phosphorus bond and use those electrons to form the pi bond. That's going to form the pi bond, but build up too much electron density around this carbon. So we're going to break the carbon-oxygen bond and use those electrons to form a phosphorus-oxygen pi bond. That will form our final alkene product. We also form triphenylphosphine oxide as the byproduct of this reaction, and that's really the driving force for this reaction. This oxygen-phosphorus double bond is very thermodynamically stable, and it's the thermodynamic sink and the driving force for this reaction forming the product. This is the mechanism for the Wittig reaction. An aldehyde reacts with an Ylide to form preferentially a Z-alkene. Here's our reaction card for the Wittig reaction. Three-phrase sentence is a reaction of an aldehyde and a ketone with an Ylide to form primarily a Z-alkene. We need to know that three-phrase sentence and all possible combinations. I'll refer you to my video on three-phrase sentences that I'll link to down below. Notes, this is a carbon-carbon bond forming reaction. You should have a whole list of carbon-carbon bond forming reactions, and this one should definitely be on there. This reaction does tend to give Z-alkenes for the traditional Wittig reaction. If we wanted something other than a Z-alkene, or if we want to work with something other than aldehydes, we might want to use one of the modifications to the Wittig reaction that's not the subject of this video. And the Ylide, if we need to make it, we can make from an alkyl halide. Tags for this reaction, it's a regioselective reaction. It really only works with aldehydes or ketones, not any of the other carbonyls, not in the classic Wittig reaction. It's a stereoselective reaction. The classic Wittig reaction gives primarily a Z-alkene, and it is technically a reduction, though I don't think I've ever really heard of a chemist talking about, I'm going to go do a Wittig reduction in lab. It does technically go from the 2 CZ bond level to the 1 CZ bond level. This is your reaction card for the Wittig reaction.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.